Hello, everyone. Welcome back. We're doing section 2 from chapter 3, and we're doing measures of variation. We're going to start with the less known one, which is the range. We don't use this very often. Range is a set of data values, is the difference between the maximum and the minimum value. So I put this list of data into my list 1. There it is, 22, 22, 26, and so on. I'm going to sort my list 1. So I'm going to hit stat, sort A, and list 1 is second 1. So there it is in order. So I'm going to take the difference between the largest data value, which in this case is 26, and I'm subtracted from the smallest, that's 22, giving us a range of 4 in this case. In a recent survey, 8 people were each asked the number of times they have been on an airplane. Here are their responses. Find the range of the data set. So we're going to find, once again, I put this data into list 2. I'm going to sort list 2, stat, sort A, and 2 is going to be second L2. So I'm going to take 26. 26 minus 9 gives me a range of 17. Now, there's limited of what we can do with the range. The more interesting measure of variation is the standard deviation. I talked about the mean in another video and how important it is. For this, standard deviation is another one of those big ones. So the standard deviation is a set of sample values denoted by, with the sample, it's going to be a capital S, and I put a little tick at the end of my S because my S's tend to look like 5s sometimes. It's a measure of how much data values deviate away from the mean. Now here's the big scary formula. Remember, this is the summation symbol. It's called sigma. And n is the sample size. The x that you see there is each data point, and the x bar is the mean of the data set. And before we jump into this, let's talk about some properties of standard deviation. Standard deviation is a measure of how much the values deviate away from the mean. The value of the standard deviation is always positive. And the unit of the standard deviation is always the same as the unit of the original data. What that means is, let's say the data are heights of people in inches. Well, the standard deviation will also be in inches, is what that means. And the sample standard deviation S is a biased estimator of the population standard deviation. I mean, it's biased because we only have some of the data. We don't have all of the data. So it's biased to the data that we actually are using to come up with a sample standard deviation. It's not an intentional bias, but we just need to be aware that there's a bias there. And we're going to find the standard deviation. Here is the good news. We are once again going to be saved by tapping stat calc and 1 bar stats. We are looking for SX. So I have put this data into my list. You can see it's my list 3. The second set of data is in list 4. So I'm going to quit out of this. You may need to pause the video, take some time to put the data into your calculator. So make sure I had that right. List 3 and 4, right? 3 and 4. So here we go. I'm going to hit stat, calc, 1 var stats, and I'm going to go up and change that to list 3, second 3, and my standard deviation, you can see is SX. You can see it right there. So S for this data is 1.673. And I'm going to do the same for stat, calculate, one variable statistics. I'm going to do this again against list 2 now. 4, pardon me. So second 4. And my standard deviation is right there. It's so nice to do all this for me. SX is 1.642. So very nicely, we can find these values fairly quickly. Now, let me talk about what the standard deviation actually is. Here's the example I'd like to give. Let's say I give a math test, and the mean score, the average score of the class, was a 70%. Let's say that the scores for the actual test, with a mean of 70%, the first one was 71, the next one was 68, next one 69, next one 72, next one 70, next one 71. All of those scores are very close to 70, the mean. So that would mean that there's a very small standard deviation. If I gave a math test and the average score was 70 and the scores were 7, 99%, 12%, 98%, you can see that those scores are really far away from the mean. That would mean that there's a very large standard deviation. All right, let's do another one. I'm going to go to my list, and we can see list 5 is this list of scores here for Susan's computer store for the 5 customers. We want to find the standard deviation based on list 5 here. So I'm going to do stat, calc, 1var stats. I need to change it to list 5, second 5. And here is my standard deviation. So S in this case is about 6.1237 is what I'm getting. Not too bad, I think. All right. I'm going to use the range rule of thumb for identifying significant values. So in general, we say that the minimum for usual values is going to be x bar minus 2 standard deviations. And the maximum for the usual is going to be x bar minus 2 standard deviations. So going up and down 2 standard deviations is going to be a really common theme in a lot of things that we're going to be doing. And so a batch of chocolate chip cookies, mean number of chocolate chip cookies is 24. So here's our x bar. And a standard deviation of 2.6. There's our S. Use the range rule of thumb to find the minimum and maximum usual number of chips, and then determine if 30 chips are usual. All right, so here's our minimum. Usual is going to be x bar minus 2 standard deviations. In this case, that's 24 minus 2 times 2.6. 24 minus 2 times 2.6. So it's about 19 chips. Our maximum is x bar plus 2 standard deviations, which is 24 plus 2 times 2.6. That's about 29 chips. 29 chips. So what does this mean? This means that if I have this batch of chocolate chip cookies and I randomly pulled one out and there were 21 chips on it, that would be totally normal. That's between 19 and 29. We're good. I reach in, I grab another chocolate chip cookie from this batch, I count the number of chips, and there are 27 chips on it. We're still good. That's within our usual range. I grab a chocolate chip cookie, I count the number of chips on it, and there are 15 chips on it. Ooh, that's below my minimum. So that's unusually small amount of chocolate chips. So when they say determine whether 30 chips are unusual, Yeah, 30 chips are unusually high, pardon me. So 30 chips is unusually, because it's above 29 chips. We'll come back to that. We're definitely going to do more with that. Range rule of thumb for estimating the standard deviation. If we don't only have like the biggest and smallest, then we find the range and divide it by 4. We'll see where the 4 comes from in just a moment. So our example here, use the range rule of thumb to estimate the standard deviation of a sample of a minimum of 19 and a maximum of 30. Well, that's going to be S is about 30 minus 19 divided by 4. So 30 minus 19 divided by 4. So an estimated standard deviation is the 2.75. Again, we try not to do estimates if we don't need to, but sometimes that's all the data that we have. All right, so some notation that we need to keep an eye on is capital S is the sample standard deviation. The sample variance is the capital S, same one, but squared. Population standard deviation is sigma. It's a Greek letter, lowercase s. Population variance is sigma squared. Some more notation that isn't here is x bar is the sample mean, and mu is the population mean. And these can get a little confusing sometimes, which is why I love this next question that ALEKS has. At the beginning of last summer, climate scientists issued a report on the thickness of the ice shelves in Antarctica. The report states that the population mean was 765 meters with a population variance of 12,100 square meters. After reading the report, Jessica wanted to verify these results. She examined a random sample of 25 of the ice shelves and found the sample mean thickness to be 780 meters and a sample variance of 11,025 square meters. So we're just going to be trying to figure out the notation here. It says that the population mean is 765 meters. The population mean, we know, is going to be the mu symbol. Population variance, that is going to be sigma squared. And the sample variance is going to be the S squared. So again, we're just getting used to the notation. And we are to the empirical rule of data. So here is a great drawing we copied from somewhere. And it says that if we go out from the mean, here's the mean, and we go out 1 standard deviation in both directions, that is going to capture about 68% of all of the data. If we go 2 standard deviations out, that's going to capture about 95%. And if we go 3 standard deviations out, which we never do, but if we did, we would capture 99.7% of the data. Now, where are these numbers coming from? We will learn when we get to chapter 6 exactly where these numbers are coming from, and we'll be able to produce them ourselves with our calculators. So using this information, on a nationwide test taken by high school students, the mean score was 48 and the standard deviation was 13. The scores were normally distributed. Complete the following statements. Approximately 99.7% of the students scored between blank and blank. Okay, so I'm going to do this. And right in the middle is going to be my mean, which is 48. And I'm going to go up 3 standard deviations. So 48 plus 13 plus 13, plus 13. Now I'm going to go 48 minus 13. To be clear, this is my mean. This is the middle. Minus 13. Minus 13. 9. Now they're saying that 99.7, that means I have to go 3 standard deviations out. See that above the purple? 3 standard deviations away from the mean. So that means the students scored between a 9 and an 87. And I know it's 3 standard deviations out because 3 standard deviations and standard deviations down. Is going to get me that 99.7. Now, if it's at 95%, then I would go from 22 to 74 and so on. So approximately what percent of the students scored between 22 and 74? And I can see right here, 22 and 74, that is 2 standard deviations out in both directions. 2 standard deviations out means that they're scoring about 95% of the data is going to be between 22 and 74. All right. The lengths of movie films that are available for streaming are modeled using the normal distribution shown below. The mean of the distribution is 189.7 minutes and a standard deviation of 20.2 minutes. In figure V, in the figure, V is the number along the x-axis in which is under the highest part of the curve. That's the mean. U and W are numbers along the axis, the same distance away from V. Use the empirical rule to choose the best value for the percentage of area under the curve that is shaded and find the values of U, V, and W. Let's start with V. V is going to be 189.7. And what I'm going to do is I'm going to keep adding a standard deviation until I get, for W, a number between 220 and 240. So let's do this. 189.7 plus 20.2. Now notice that's not between 220 and 240. So I'm going to add another standard deviation, plus 20.2. There it is, 230.1. And this distance here is 2 standard deviations out. Let's go down. Let's start at the mean, 189.7 minus 20.2. 169.5 is not between 140 and 160. So I'm going to subtract another standard deviation. Now we're here, 149.3. And once again, we are exactly 2 standard deviations away. So if we are 2 standard deviations away, I'm going to go back to my empirical piece here. We can see that means that we're at 95%. That's the answer there. I hope that was helpful.